So, last time we were looking at unidirectional transport in a Cartesian coordinate system, where there is variation in the fields, temperature, concentration or velocity fields in only one direction, which we had considered to be the z direction. Okay. In a Cartesian coordinate, where the surfaces of constant coordinate are planes perpendicular to the z direction. Okay. And in order to derive the conservation equation, we had considered a differential volume. Okay. A differential volume bounded by surfaces of constant coordinate. Okay. So, in general we have a configuration where we have two locations, two boundaries in this Cartesian coordinate system, where either the properties or either the fields or their derivatives are fixed, and initially the value is specified. In addition, there could be some production of mass or energy which is also specified. And we derived an equation for this by considering a differential volume bounded by surfaces of constant coordinate. Okay. Two surfaces separated by a distance delta z in the z direction. The z direction is the direction in which there is variation, okay, of the concentration, temperature or velocity fields. And the basic equation is the same. Okay. Change in quantity in a time delta t, okay, is equal to quantity in minus quantity out plus the production of quantity, okay, in that time delta t. Okay. If that quantity is mass, then the change in mass in times delta t is equal to the mass at times t plus delta t minus the mass at time t, okay, times the volume. Sorry, the mass difference in mass between the time t plus delta t and t. That is the difference in concentration between the time t plus delta t minus t times the volume. Okay. So, the concentration times volume is the mass. Okay. The mass in and the mass out are products of the fluxes and the area and delta t, okay, because flux is transport per unit area per unit time. So, the mass in and the mass out is equal to the flux times the area times delta t, and the production in differential volume is a production density, production per unit volume per unit time, okay, into the volume into time. Put all these into the conservation equation, okay, divide throughout by volume, divide throughout by time, and take the limit as delta z goes to 0, delta t goes to 0, you will get a differential equation, okay, for the mass, momentum or energy. Okay. The differential equation contains the derivative of concentration with respect to time, the spatial derivative of the flux and the source term. If you use the constitutive relation, okay, so I told you that when we derive conservation equations there are two inputs. One is the balance condition, okay, which I just highlighted for you over here. This is the balance condition, and then you require a second input, and that is the constitutive relation. In this case the equation for the flux is the constitutive relation. Put them both together and you get a differential equation, a diffusion equation, okay, which contains a derivative of concentrations with respect to position and with respect to time, where d is the mass diffusion coefficient. If that diffusion coefficient is independent or is a constant, then the differential equation reduces further. Okay. And we had derived this for mass, we had derived this for energy as well. Okay. So, okay, partial C by partial T is equal to minus partial Jz by partial Z plus S, okay, partial H by partial T is equal to minus partial Qz by partial Z plus energy source. Okay. This is the differential what you get from the differential balance. Okay. And here you have to use the constitutive relation, Fick's law for diffusion or Fourier's law for heat conduction, okay, and in this case also I have to substitute for the enthalpy density in terms of temperature. Okay. And then I will get differential equations. Partial C by partial T is equal to minus there should be no minus sign here because there are two minus signs in each of these equations, and they will multiply to give you a positive sign. Okay. Okay. And in the energy equation, I said that if the density and Cp are constants, that I can divide throughout to get alpha. Alpha is K by rho Cp plus Sc by rho Cp. Okay, I think I had forgotten this in the last lecture to divide throughout by rho Cp. So here you should get by rho Cp here. Okay, kindly make that correction, okay, in the last lecture. Okay. And then if I will get dC by dt is equal to d partial square C by partial Z square plus S, and dt by dt is equal to alpha okay. So these are the two forms of the equations. Okay. There were two approximations here. One was, okay, from going here to here, we had assumed that rho Cp is equal to constant. Okay. And going from here to here, we had assumed that d alpha are constants. This first condition is actually followed in many practical applications. Okay. For an ideal gas, for example, Cp is independent of temperature. Okay. The specific heats are independent of temperature, and if the gas is incompressible, then the density is independent of temperature. A fluid can be considered incompressible if the flow velocity is much smaller than the speed of sound or the molecular velocity. Okay. A fluid can be considered incompressible if the flow velocity is much smaller than the molecular fluctuating velocity or the speed of sound, okay, because density variations in the form of shock waves travel at the speed of sound. So long as the flow velocity is much smaller than the speed of sound, the density is a constant, and the specific heat is actually a constant in many situations. Okay. For ideal gases, it is a constant. Okay. It depends only upon the degrees of freedom, okay, of the gas. Okay. For real gases like air, Cp varies by about 1% for 0 degrees centigrade to 100 degrees centigrade. Okay. So, there is only a 1% variation in the specific heat for even a real gas like air at standard temperature and pressure over a temperature range of about 100 degrees centigrade. So, in that case you can actually assume that Cp is a constant. Similarly, in water, Cp varies by about 0.1%. Okay, it is 1/10 of the variation in air. For 0 degrees centigrade to 100 degrees centigrade. Okay. So, the variation in specific heat in practical applications is actually quite small. Okay. So, this approximation is actually a good one. Okay. You can assume that the density and specific heats are constants. Okay. The thermal diffusivities and the mass diffusivities, those are not in general constants. Okay. So, we saw when we discussed diffusion and dispersion, the thermal diffusivity and the mass diffusivity in gases are proportional to the absolute temperature to the half power, okay, square root of the absolute temperature, if the gas is a hard sphere gas. So, in that case, the variation in the diffusion coefficient will scale roughly as the variation in temperature divided by the absolute temperature. Okay. So, you require the variation in temperature to be much smaller than the absolute temperature to consider the diffusion coefficients to be a constant in gases. Okay. In liquids, for example, in water, the thermal conductivity varies by, so let me do it for air first. Okay. By 30% for 0 degree centigrade to 100 degree centigrade. Okay. And in water, the thermal conductivity varies by 20% for 0 degree centigrade to 100 degree centigrade. Okay. So, this approximation one has to be careful that the diffusion coefficient is a constant. Okay. In real situations, if there is a significant variation in temperature, there could be a significant variation in these diffusivities, and because of that we cannot reduce the equation to this form in general. Okay. We have to make sure that the variations in temperature are small, so that we can make this reduction. Okay. In real situations, for gases the temperature variation has to be much smaller than the absolute temperature. For liquids, the temperature variation has to be sufficiently small that the conductivity or the mass diffusivity does not change very much. Okay. So, those are the diffusion equations for mass and energy. Finally, I will come to momentum. Okay. I have two surfaces moving with velocities v naught and Vh separated by a distance h, okay, due to which there is some flow field in this, okay, between. So, this is the z coordinate, this is z is equal to 0, z is equal to h. Okay. And the balance equation is slightly different from what we had earlier for mass and energy. The balance equation comes out from Newton's law, okay, for Newton's law of motion, okay, that the rate of change of x momentum is equal to plus sum of forces. Okay. So, we take once again a differential volume. Note that momentum is a vector and the balance that we are writing here is for the x component of the momentum. Okay. Momentum is a vector which has 3 components, and here we are writing the equation for the x component of the momentum. Okay. This is the location z, This is the location z plus delta z and the height is delta z. And we are assuming that there is no variation in the direction perpendicular to the x direction. Okay, so now the forces that are acting in the x direction, okay, the forces that are acting in the x direction, okay, there is a pressure force that will act inwards at the surface on the left, okay, and a pressure force that will act rightwards on the surface on the right. Okay. And there are stresses that will act on these two surfaces. Okay. Okay, the surface on top, the unit normal is in the plus z direction. Okay. The unit normal is in the plus z direction. Therefore, the stress exerted, force per unit area at a surface whose outward unit normal is in the z direction is the shear stress tau xz. Okay. The force exerted at a surface whose outward unit normal is in the plus z direction, tau xz, where x is the direction of momentum and z is the direction of variation or the direction of transport. At the surface below, the unit normal is in the minus z direction. Okay. Therefore, the force exerted on this surface is equal to minus tau xz. Okay. Because if you reverse the direction of the unit normal, the direction of the force reverses. On both sides of a surface, the forces have to be equal and opposite from Newton's third law. When you reverse the direction of the unit normal, right, you are reversing the volume in which you are calculating the force, the side of the surface on which you are calculating the force. Therefore, when you reverse the unit normal, the sign of the stress reverses. Okay, so it is in the minus z direction. Okay. So, what is the rate of change of momentum? Is equal to the momentum density rho Vx at z t plus delta t, the change in the momentum density between the time interval t and t plus delta t times the volume, which is A times delta z. Okay. Change in momentum density times A times delta z. And I will assume that the density is a constant here, it is an incompressible fluid. Okay. Momentum in. Okay. There is momentum in because there is flow of fluid into this differential volume at the left surface. Okay. Momentum in because there is input of fluid at the left surface, and momentum out because there is momentum leaving the fluid on the right surface. However, we have assumed that there is no variation in the direction perpendicular to z. Okay. So, for this particular differential volume, for the x momentum, the momentum in has to be equal to the momentum out. Okay. The momentum in has to be equal to the momentum out for this particular surface, because there is no change in the velocity between the left and the right surfaces. Okay. Even though there is momentum coming in on the left, the velocity on the left is the same as the velocity on the right. Momentum in is the same as the momentum out. Momentum coming in is the same as momentum leaving. So, in this particular case, momentum in and momentum out are the same. Okay. Forces. Okay. As I said, there are pressure forces perpendicular to the surface on the left face and a pressure force perpendicular to the surface on the right face. The pressure is compressive. Okay. So, the pressure is compressive. So, the pressure on the right force will act in the minus x direction, whereas the pressure on the left face will act in the plus x direction. If you recall, pressure always acts along the inward unit normal. Okay. Pressure is a compressive force at a surface, it always acts in the direction perpendicular to the surface, inward to a differential volume. So, on the right side, the inward unit normal is in the minus x direction, left side it is in the plus x direction, and therefore, those will cancel out, and therefore, there will be no net pressure force acting on this surface. because there is no variation in the direction perpendicular to z. Okay. There is no variation in the direction perpendicular to z. So, the pressure acting on the left face and the pressure acting on the right face are equal in magnitude and their directions are exactly the opposite. Okay. And because of that, there will be no net force due to the pressure forces acting on the left and the right side. Okay. And then there are stresses that are exerted tangential to the surface at the surfaces z and z plus delta z. Okay. So, the tangential forces okay, so the as I said, the force at the location z plus delta z, the unit normal is in the plus z direction. Therefore, this force is equal to the shear stress. Stress is force per unit area per unit time. Okay. I am sorry, the stress is a force per unit area. Okay. And therefore, the force exerted, okay, the force exerted is equal to the shear stress into the area. I made a mistake here. If you recall, in this rate of change of momentum, change in momentum is what I had written on the right side. The rate of change of momentum is this whole thing divided by delta t. Okay, rate of change of momentum is change in momentum per unit time. Okay. So, the rate of change of momentum at the time t has to be equal to the momentum at time t plus delta t minus that at t divided by delta t. Okay. So, the shear stress at the surface with unit normal Ez plus Ez is tau xz, where tau xz is in the plus x direction. Okay. The force at the surface, okay, these are both surface forces, forces acting on the surface, the shear stress and the pressure. Pressure sum to 0, shear stress does not necessarily sum to 0 because there is a variation in the z direction. Okay. So, this one is tau xz at z plus delta z times A, and this is tau xz at the location z times A. Okay. So, the sum of forces I had separated out into pressure force, okay, which turned out to be 0 because there was no variation perpendicular to the z direction, plus shear force. Okay. These are both surface forces, they act at surfaces. I could also have a third term which is what is called a body force. Okay. These are forces like gravity, for example, which act throughout the volume. Okay. The force on a volume element of fluid is going to be proportional to the volume element itself. Okay. So, for example, the gravitational force, okay, okay, the gravitational force, for example, is equal to rho g into delta z into A. Okay. Rho into volume, A delta z is the mass times g. Okay. Rho g into A delta z. Okay. So, the body force typically has the form something, a force density times the volume. Okay. Has the form of a force density times the volume. Okay. So, I will write this as Fx times delta z times A, where small fx is the force density in the x direction. Okay. So, if you had a component of the gravitational acceleration in the x direction, the force exerted on this due to the body force is going to be equal to Fx into delta z into A. So, those are the forces that are exerted. Okay. The momentum in and the momentum out due to the fluid flow, they cancel out. Surface forces are of two types, pressure and shear stress. Pressure on the left and right faces cancels out in the x direction because there is no variation there. The shear stress acts on the top and the bottom surfaces. There is a variation in the z direction, and therefore, the shear stress does not necessarily cancel out. So, we will put all of those together, okay, in the momentum balance equation. Okay. Rho Vx at z t plus delta t minus rho Vx at z t a delta z by delta t is equal to a into tau x z at z plus delta z minus tau x z at z by, oh, that is all, plus the body force F x a into delta z. Okay. So, this is for the total momentum. To get an equation for the momentum density, we have to divide by a times delta z. Okay. To get an equation for the momentum density, we have to divide by a times delta z, and I will get rho into Vx at z t plus delta t minus Vx at z t is equal to tau x z at z plus delta z plus Fx, where Fx is the force density. This is the difference equation for the momentum density in the x direction, and to get a differential equation, take the limit delta t goes to 0, delta x z goes to 0. Rho times partial Vx by partial t is equal to partial tau xz by partial z plus Fx. And then I can use Newton's law for viscosity in order to express tau xz in terms of the velocity gradient. Tau xz is equal to mu partial Vx by partial z. Substituting that, I get rho times partial Vx by partial t is equal to partial by partial z of mu partial tau xz by partial z, sorry, plus Fx. I can divide throughout by density. Since we are considering incompressible flows here, I can divide throughout by density, and I will get partial Vx by partial t. If density is a constant, d by dz of the kinematic viscosity times partial Vx by partial z plus Fx by rho. Momentum conservation equation, and as you can see, this has the same form as the mass and energy conservation equations. You substitute the velocity in the x direction for the concentration, the kinematic viscosity, momentum diffusivity for the mass diffusivity, and the body force density for the production of mass, and you will get this momentum conservation equation. Okay, so it has exactly the same form. The other thing I would like you to note, okay, if you recall, when we had written the equation for mass balance, for example, we had partial c by partial t is equal to minus partial j z by partial z plus source, and the equation Jz is equal to minus d partial c by partial z, and then I got the equation of the form partial c by partial t is equal to partial by partial z of d partial c by partial z plus source. Okay. Note that there was a negative sign in this equation which is not there in this equation. Okay. Negative sign in the constitutive relation which is not there in Newton's law because of the difference in the convention for the direction of the flux and the direction of the force. Okay. But despite the difference in the negative sign in each of these, the final equation that is written in this form turns out to be exactly the same, whether it is for mass conservation or momentum conservation. Okay. So, I had discussed this in some detail when I discussed the Fourier's law, Fick's law and Newton's law. Fourier's and Fick's law have a negative sign, Newton's law does not. That is because of the difference in convention. For Fourier's and Fick's law, the flux is positive if it is acting along the plus z direction. For Newton's law, it is positive if it increases momentum of the volume below. Okay. But despite that, the form of the final conservation equation are exactly the same. Okay. I will continue this, give you a brief summary of these conservation equations before we go on to solving steady state problems. Okay. So, I will continue this in the next lecture. I will see you then.